Hey everyone, my name is Angelo Mali, and this is a video assignment for CS223B, a computer vision class at Stanford. In this video, I'm going to be looking at a very specific computer vision technology called face detection. Face detection is actually pretty popular today, and in fact you may have seen it already in your digital cameras. So this is a new digital camera from Canon, and it uses face detection technology to look for faces in the frame. For example, here it actually puts a box around my face and focuses on the specific image in that box and before it takes a picture. That is one application of face detection technology today, but in fact this is also used in many different applications such as surveillance. For example, you can use the face detection technology to look at the faces in a frame of the video sequence or just still images and compare the faces that are detected onto a known database of faces and find out whether any of those faces match together. Now this is important in the movie Transformers because in the movie Transformers the Decepticons are trying to find a Sam Witwicky because he knows where the location of the cube is. Also, the Transformers are trying to find Sam Witwicky to protect him against the Decepticons. So in this video, we're going to be looking at the face detection technology used by the Transformers and Decepticons, and then we're going to be looking at the little things, the math behind the face detection technology. And then we'll see whether it's possible today to use this technology in the movie Transformers. So first, let's take a look at a specific sequence from the movie Transformers. In the movie, we saw that the Decepticons use Sam Witwicky's email profile image as their basis image for detecting Sam. Now let's take a look at this picture again. So do you think this image is enough to detect Sam Witwicky? What if he fixed his hair, or closed his mouth, or wore sunshades? It would be quite difficult to look for Sam using that picture alone. What the Decepticons and Transformers need is a face space. Not Facebook, not MySpace, face space, a collection of eigenfaces. Now let's look at the concept of eigenfaces, which is the math behind face detection today. Face detection is possible today because of linear algebra. We use the concept of eigenvectors, wherein a given set of independent vectors, Vi, any other vector can be projected onto its range space by using the least squares method. Face detection follows accordingly, in that given it an image of a face, we can project it onto a set of independent face images. If this set of face images is a good set, then it is possible or reasonable to expect that any human face image can be reconstructed as a linear combination of these images with reasonable accuracy. The elements of such a good set of images are called eigenfaces. Eigenfaces serve as a representative sample of human face images in that they capture the main characteristics of a human face. The linear combination of these eigenfaces make up what we call the face space. Not Facebook, not MySpace, face space. In short, eigenfaces are eigenvectors derived from a specific covariance matrix of these high-dimensional vectors of possible faces of human beings. This is the definition from Wikipedia. The method of finding these eigenfaces is called principal component analysis. So how do we perform principal component analysis? How do we set off on finding these eigenfaces? Here, we're going to be talking about solving for eigenfaces, and we start with recognizing that faces can be represented as a vector. Faces like Sam Witwicky's picture here is an image of a 200 by 300 pixel image. These images lie on the R space of 200 by 300, and we can represent them as a vector of length 60,000 of column 1. If we are going to find eigenfaces, we need to start with a set of images or faces. These faces have to be aligned with the same pixel size and of the same lighting to standardize on the similarities of the faces. If we are going to use Sam Witwicky's image in the previous slide, shown here on the left, then all of the other images in this set must have the same pixel size, 200 by 300, same alignment of the eyes, and same lighting. Once we have a set of images that are transformed into vectors x, we then calculate the mean or the average of these vectors and represent it as mu. We will use this mu to build our covariance matrix, S of t. This is the matrix that we will use to solve for our eigenvectors. In this slide, I'm showing you the formula of how to calculate the covariance matrix. Once we have built the covariance matrix S, finding the eigenfaces or the eigenvectors of the matrix S simply becomes a least squares problem. Least squares is a very well studied topic in linear algebra, and one way to solve this is by solving the singular value decomposition of a matrix. In the singular value decomposition of the matrix S, we will have to compute for a matrix of the size 60,000 by 60,000 if the images we use are 200 by 300 pixels. If we get bigger pixels or images than this, then the computation of the singular values would be much more than just a simple linear algebra problem. It would require signal processing sophistication and a very fast processor. Once we have calculated the eigenfaces, let's take a look at how they look like. In the image below, X bar shows the average of all the images that we have sampled. V1 being the very first eigenface, V2 the second, V3 the third, and so forth. You'll notice that V1 being the very first eigenphase shows the most common features available in all images of our set. In this case, it shows the skin color. V2 becomes a little bit more particular in the details, and it goes down until you see at the bottom right where the details are more pronounced. These eigenfaces are basic principal components of the human face. We will use combinations of these to build projections of faces and estimates of other faces. So here's a comparison of faces versus eigenfaces. Faces are images we take of people, and eigenfaces are faces we compute out of scatter matrices. The beauty of eigenfaces is that it can represent any image on the left or any face by just linearly combining or adding all these eigenfaces together. The eigenfaces, again, give us the principal components of the human face, and we can add them in various amounts to build any face on the left. So how do we go about detecting Sam? First, we do the projection of Sam onto the eigenfaces and see if this projected image from the face space is close enough to the actual image we just saw of Sam. If the difference between these two images is within a threshold, then we're able to define and find Sam. That's it. That's how we go about detecting faces today.
This thing is wicked.
Help me out late at night. Extreme places I had gone.
they never see any light. Dirty basements, dirty noise, dirty places coming through. Extreme worlds alone. Did you ever like it,